Awesome. Okay. So, uh, welcome everyone. I'm gonna talk about computer graphics and rendering. Um, this is the only slide that has a nice background. Uh, a lot of the slides are drawn by me, so there's a little bit of I don't know if it's super duper high quality the pictures or whatever, but hopefully it'll get the point across. Um, so first, we should talk a little bit about linear algebra, because it's not a required course for computer science here at Towson. It's sort of required for computer graphics. It only like very basic linear algebra though, so it's stuff that you can teach yourself. The main concepts that you really need to know are that vectors are just basically lists of numbers. They're written mathematically as column vectors, at least in America. There are places in Europe that do things by row major ordering, but that's not all that important. Um, and they're just uh, they can represent a lot of different things, but for a lot of this, you'll see that they represent either positions or directions. Um, so a vector just describes uh, a distance in the x direction from the origin, distance in the y direction from the origin, and then for 3D vectors, a distance x, y, and z. Um, Adding vectors is pretty simple as well. So you've got this 0 in the x direction, 1 in the y direction. If you add that with a 1, 1 vector, then you get 1, 2, and you just add the numbers uh, x to x and y to y, and that gives you a new vector. Um, Multiplication's a little bit different. So when we multiply vectors together, we do what's called the dot product. And so we then make this sort of like a row vector and this column vector. And we basically multiply this first element by the first one and the second element by this second one. And then we add those together and we get just one number back. That's important because matrices, which are kind of like lists of vectors, are usually what we use to transform vectors. So if we were to multiply this vector 1, 2 by this matrix 1, 0, 0, 1, a matrix in this form where there are zeros everywhere and just ones in the diagonal is called an identity matrix. And that's because when you multiply a vector by the identity matrix, you'll get the same vector in return. You do this 1 times the 1, this 2 times the 0, and you add those together. 2 times 0 is 0, 1 times 1 is 1, and so you get 1 back. And then 1 times 0 is 0, and then 2 times 1 is 2. You add those together and you get 2 back. If you have it in the minor diagonal, you have 1s, you'll get this vector flipped upside down because you get this component, and then the 0 negates this first one, and that'll give you the 2. And this one, you'll get the 1 back. And then for other vectors, you can get something completely different back. You just have to multiply first by first, second by second, add those together, and put that in the first position. And then for the second row, you do the same thing, and then you get the second element of the vector. There's a little bit of a difference in the linear algebra, in the way that we use linear algebra in graphics. So if you were to have if you wanted to describe a direction or a position, it might look the exact same if you just use 3 coordinates for a 3D space. So what we do is we use 4 coordinates, making it 4D space. And we use a 0 for the direction vector, and for a vector that describes position, we put a 1 on the end. The reason for that is because vectors mathematically always represent a distance from the origin, but we're not trying to do that with a position. We want to be able to translate that position in space. And translation in space is not a linear transformation. So because it's not a linear transformation, we have to basically put everything in the context of 4 dimensions, 4 spatial dimensions, for a transformation in 3 dimensions, or for a translation in 3 dimensions to be a linear transformation in 4 dimensions. We call these homogeneous coordinates, or homogeneous coordinates. I always say homogeneous, but that's actually not how it's pronounced. So there are 4 main types of rendering algorithms. Hold on, I need a drink. There are there's a polygon rasterization algorithm. There are voxel rasterization algorithms. There's ray tracing algorithms, and there's ray marching algorithms. Polygon rasterization and voxel rasterization are similar in that they both use the concept of rasterization. Ray tracing and ray marching are very similar as well, but we're not actually going to talk about those in this presentation. We're going to specifically talk about polygon rasterization because it's the most commonly used. Voxel rasterization is very similar. It just has a lot of extra, there are a lot of extra like optimization steps because everything's a cube, or some sort of like rectangular prism. So why do we use polygons? Well, we need a way of, that should have said why triangles. So the polygon that we use is triangles. We have a few different options of polygons, a lot of different options of regular polygons. We could use a hexagon, we could use a square, we could use a triangle. Maybe we could even use a line. The problem is that, first of all, these two are too complex. We need a way of describing an area in space that we can put color on, right? Lines don't have any width, so we're not going to get an area out of those. And these are too complex because we can describe 3 points is the least amount of points that you need to describe a plane in 3D space, right? And so as you can see here, the line is too simple. So instead, we use triangles. Now we're going to take a little sidestep, and please use the chat and tell me if I'm going too fast. So I've got like a lot of things that I want to say, but not a lot of time to say it in. We're going to take a sidestep though and talk about how what happens when you want to render something. So data is stored in your computer in memory as bits, like ones and zeros and stuff. So it's numbers effectively. So how do we get that into colors that show up on your screen? Well, first we do some math and we send it to the GPU. The stuff, the math we did to the data, the output of that gets sent to the GPU, where the GPU does more math and some magic. and then it sends it to the display. What happens in the GPU is we send the data to GPU memory. We just store it there. And then we set up some of the configuration on the GPU so that it knows how to do the different steps. We tell it it's normally like a state machine. So we give it, we set its state, and then it'll have, all these different potential ways that it can make the geometry. So we set up how it should make geometry. We'll have like points represented by floating point numbers in 3D space. We give it those points, it connects the dots. Then we have some textures. We first it rasterizes, and then it applies those textures to the rasterized image. Now, rasterization is taking these potentially infinitely precise points in 3D space and quantizing it into pixels. So we figure out what portions of the shape this pixel makes up, and then whatever is the largest amount, or whatever is the color that takes up the most space in the pixel that's what we color the pixel as. So the way that geometry is modeled and the way that we send the geometry data to the GPU is we will have a model, which is sort of like a structure that is a collection of meshes. Meshes are like collections of triangles, which are collections of points. And those points are a collection of 3 coordinates, X, Y, and Z. These triangles are a collection of 3 points, right? So a point A might have X, Y, and Z as its coordinates. It might be part of this triangle ABC. And it's important how we define the order of these points. It doesn't exactly matter whether you choose to go with a clockwise or counterclockwise winding order, but you just need to be consistent, because the winding order, or the whether we go clockwise when we list the points, or we go counterclockwise when we list the points, that determines which way the triangle is, like where the front of the triangle is facing. That's important for a technique called backface culling, where we only render the front of any triangle, because the backside of the triangle isn't supposed to be viewed by the camera. So that side doesn't need to be rendered. So triangles are built into a collection of meshes, and often these triangles share a ton of points, right? Like 1, 2, 3, 4, 5, 6 triangles share this one point. So often we don't represent triangles as a list of these points specifically. We will have a list of indices. We'll have like one array of points that lists every individual point that makes up our geometry. And then for all of the triangles, we will list an index into that array of points. We'll list 3 indices into that array of points that defines the triangle. That just helps save space, because you can have a lot of points in a mesh or in a model, right? And this model that I'm showing here is could be a collection of, say, just the nose cone could be one mesh, and then all the way back here, each fin could be a mesh, right? Or it could just be that there's one mesh for a fin, and then we translate like the position and orientation of that fin and reuse that same mesh in describing the model. So everything's very modular and kind of uh, gets built one on top of another and then stuck together. It's a lot like it should be very familiar to people who are used to doing object oriented programming and design, because often you'll compose a bunch of different elements in describing a larger system or object. So more specifically, this is kind of a layout of what we put into GPU memory before we tell it to render things. We give it we give it a set of instructions, and we give it a set of uh, data. The instructions can be split into two categories: commands and programs. Commands tell the GPU what to do in a way. So they set up state. They tell the GPU in what order to do certain things, and how to associate or yeah, how to associate the data we're about to give it. And then programs uh, tell the GPU how to draw the data that we give it. The data that we give it is vertex data, which describes those points. But it's more than just positions. Vertices can also have things like normal values or UV coordinates for textures, things like that. So normal values are used for lighting usually, and they can be used for other things, but the surface normal of a triangle is it's just a vector that points in the direction away from the face of the triangle. So wherever the front of the triangle is, like out from that. And that helps you when you're trying to have like certain kinds of reflections and stuff like that. It helps you do the math for how does the light bounce off of that thing, off of that triangle. And then UV coordinates we'll get into in a bit, but they're used for when you want to apply a texture to a triangle. And they're used to the way that you put them into the GPU is you're describing basically a place on the texture where that like a pixel on the texture where that point would be. So you can take a small subsection of the texture and have that be what is laid over your triangle, rather than the entire texture being used or the entire image being used for that triangle. Attribute descriptions tell the GPU the way that we've laid out the vertex data. So what sections of the vertex data should be bundled together. The 3 coordinates could be one attribute, and then the the direction of the normal vector could be another attribute, and then the UV coordinates for the texture could be another attribute. And we use that that way we can have all of the vertex data in one contiguous place in memory, which makes it way faster to access that data. And we can still split it up in the way that we need it in the programs that we send to the GPU. Index data, I talked about how the triangles are usually described as indices into the array of vertices. And so that's what the index data is for. Light data usually is passed into the GPU separate from all of the vertices, even though the way that the light affects the objects will be different depending on where they are. The lights often won't change position. So all we need to do is have that set of data for all of the scene's geometry. It doesn't need to change for each different geometry. And so we pass it in separately. Textures are basically the same thing. We'll pass in textures, but those textures don't change from between objects. And the reason for that is because different objects might use the same texture. So we don't want to keep passing in the same data over and over again. So instead, we create what are called uniform buffers, which are data buffers that persist over all of the programs that we send to the GPU for that frame. And then there's some other miscellaneous data we can add. And then there's in the GPU, we'll have frame data, which is created and maintained by the GPU on its own memory. And that's where we get back all of the color values and stuff that we need to know. So the frame data can be the color buffer, which is just the array of all of the pixels that get drawn to the screen. The depth buffer, which is it's similar to the color buffer in that it's the same size as our screen, but each pixel instead describes the depth of the object that pixel is getting its color from. So how far away from the camera it is. That's useful information because it allows us to throw out data for certain objects that are occluded by other objects in the scene. So if something's way closer to the camera, it might be blocking your view from a few different objects behind it. And if we already know how close that object is to the camera, any of the objects that are directly behind it and completely obscured from our vision can just be disregarded by the renderer, and it doesn't have to do any calculations for those objects. And the stencil buffer does something sort of similar to the depth buffer, but instead it's user defined, or programmer defined, I guess. So the programmer will write into the stencil buffer what pixels he wants to make a stencil for, right? And it's kind of like how a stencil works when you're using it to draw, when you're using like a stencil to draw on paper. you can either draw inside of that stencil, use that stencil to define an area that gets drawn inside of, or you can use it as a way of blocking the GPU from drawing into uh, that stencil. So it's just used to define a draw region for the frame buffer. Well, before we get into that, I want to talk for a second about these programs. So these GPU programs, they're the main programmable part of the graphics pipeline. And so we can write shader code for the GPU and then send the source code for that into the GPU. And it will compile and link, well, the API will compile and link it and send it to the GPU. And then the GPU will use that as instructions for when it does certain shader passes during the draw time. So once we've given it all of the vertex data and all of this data, it will start by running a vertex shader program, which tells it how to interpret the vertex data and what to do with that information, and then what to pass on to the next part of the pipeline. And the next programs and the next programmable parts of the pipeline are the geometry shader and the tessellation shader, which I won't go into too much detail about, but they sort of transform the vertex data, add to it or take away from it once it's passed into them. And then once it goes through those, it gets to the rasterization part of the rendering algorithm, which is where it first it projects the 3D space into 2D, which we'll talk about in a few slides. And then it makes it, and then it turns that projection into a rasterized image, so an image of pixels. And then it passes that to the pixel shader or the fragment shader. It's called different things in different APIs, but I think pixel shader works better because it tells you what it does. It's a program that runs for every pixel that gets drawn to the frame, and it decides how the color should be decided for that pixel. So you can say have a certain position or a certain like area of the geometry that you don't want to draw normally. Say you want that to just be a solid color, and you could decide that in the pixel shader. The pixel shader is also where you do almost all of the programming for ray tracing. And then there's another type of shader program that you can write, which is called a compute shader program. That's for general purpose data, like it's for computing general purpose data, things like large data sets, or where maybe you're trying to make a machine learning sort of application, or do some I don't know, deep neural network thing. You've got this gigantic array of data and you need to process it, but it's not that uh, every like element of that data necessarily depends on any other element in that data. So you can parallelize the computation, and that's what GPUs are really good at. Uh, and so you'll use a compute shader to do that sort of thing. So before we get into projection, we want to think about how much like our eyes can see, right? We can't just see 180 degrees. I don't know if it's exactly 90 degrees that we can see, but that's often the default for um, a lot of graphics programs, and I think it's good enough. Like it makes a nice image, so that's usually what I use. Um, what we have to worry about is how does that affect what we can see? So if you're doing an orthographic projection, you'll have this on the top of this slide, the rectangular prism or whatever, where everything that's in front of the camera just gets smushed down onto the plane that's closest to the camera, and that's what you render to your screen. Uh, but that's not how we see most things. We see things with a field of vision um, or field of view that is sort of like an angle and describes almost like a cone that comes out from our eyes over a certain distance and space. To emulate that, we use what's called the view frustum. And a view frustum uh, is just like a cone or a pyramid with the oh, okay. Have a good day. Sorry. Uh, the I just I want to make sure to check the chat every once in a while. So when I see that someone's put a message there, I'm gonna stop and look at it. Um, so this view frustum is just like a pyramid with its top chopped off, and this near plane, the the plane of this frustum that's closest to the camera, that's going to be what we project everything onto, and it's uh, going to be used as uh, basically the plane that describes this the 2D viewport of our uh, display. So we need quite a good bit of information to figure out how to map all of the space that's inside of this frustum. By the way, this far plane is the cutoff, so we don't render off into infinity. We stop at a certain distance, and that's what the far plane is. So we've got a view distance that goes from the near plane to the far plane, which describes uh, the depth, uh, the maximum depth that we can render to. Anyway, we need a good amount of information to correctly project things onto this screen. Uh, one piece of information is the the angle of our field of view. Uh, another one is where the near plane is. So it's almost always exactly distance 1 in the z direction from the camera. And then uh, we need to know how far away the far plane is. Uh, and we need to know the aspect ratio of the screen. So this is a good picture that kind of labels everything you really need to know, right? So you've got a point XYZ, and we want to see where it maps to when it's projected onto this near plane. And this is at Z near, so the near plane Z distance. we've got half width and half height of the near plane, which is important to know in conjunction with the field of view, the angle for the field of view, because we need both of those things to determine the size of the far plane and to get our scaling factor for, as you can see, like this isn't the same X and Y position as this is, but if we were to make it like the point XYZ, I don't know if you guys can see my cursor. The point XYZ and the point and the projected point X projected, Y projected, Z near. Those 2 points aren't in the, oh, sweet, thank you. So those 2 points aren't in the same X and Y coordinates. To figure out what X and Y coordinates is going to be at in this plane, you can think about it as if you were to make a section of the frustum exactly at Z of this XYZ point coordinate and figure out the normalized distance of that point from the center of the plane. So if say width is 20, then you've got half width as 10, and say height is 20, just to make it easy. So we've got half width and half height are each 10, and you've got a point at like 7, 7. If you go out to here and say it's half width and half height are 100 by 100, that would mean that this point would have to be at 70, 70, because it's the same ratio of the half width and half height to the coordinate location of the point. The way that we project things is we've got local space coordinates, which are if you've got an object, right, like a model, you have its own local coordinates, which is what we use to describe the vertex positions of that model. So when we move that model, like we translate it around in 3D space, the local coordinates don't change, but its origin location sort of does. So we apply a world space projection or a world space translation matrix to each of those objects. We call it the model matrix, and that shifts all of the vertices in its local coordinate system to the world space coordinate system, which is shared by all of the objects. Once we've got everything in world space coordinates, we then figure out what they are in clip space. Clip space coordinates are usually, so they're the same as world space coordinates, except it's all translated by where the camera is. It's also called camera space coordinates. So the camera becomes 0, 0, no matter where the viewer is in the world. And we just shift everything around if we shift the origin to 0, 0, or if we shift the origin 0, 0 to where, like, to the position and orientation of the camera. Once we've got clip space, we then transition into normal device coordinates. Normalized device coordinates are if you think about this view frustum being everything that we can see in the scene, um, we turn this view frustum into, we squish it down into a 1 by 1 by 1 cube. And that's really hard to like, it's kind of hard to describe all of the math that goes into that and would probably take near an hour on its own. So uh, I'm going to skip over that and skip over how we go from normalized vice coordinates to screen space, because I've sort of already described the idea behind projection, and instead show you this perspective projection matrix, which is what we apply to the clip space coordinates to get back the coordinates we need, or the coordinates that describe where we are in uh, the viewport, so where we are on the screen. As you can see, it's sort of complicated, but sort of not complicated. Like, it could be a lot more complicated, but there's a lot of stuff here. You see, we need the FOV. We need the distance to the far plane, the distance to the near plane. We need the aspect ratio of the screen. And that's about all we need. That's kind of all that goes into this. Now we're going to talk about how we apply textures to triangles. So I know this is sort of really disjointed, but there are a lot of there's a lot of concepts to go through, and they're not all necessarily super connected. So I apologize for that, but I wanted to be able to get through each entire concept without like trailing off into one direction and then come back later and expect you to like remember every word that I said like 30 minutes ago. So barycentric coordinates describe coordinates inside of a triangle. They're really useful because if we know where a triangle is on the screen, if we've projected a triangle onto our screen, right, we then, and we know the A, B, and C coordinates for its like its vertices, we can figure out a point P inside of that triangle, or we can represent a point P inside of that triangle as a combination of the coordinates of A, B, and C with different weights, which we'll call U, V, and W. Each of these is just a single number, and when you add them together, they equal 1. So normally we only use 2 coordinates. I've said it before as U, V coordinates. So what do we do with W? Well, because we know W equals 1 minus U minus V, because U plus V plus W equals 1. As long as U is more than or equal to 0 and V is more than or equal to 0, which it will be, because if the point isn't within this triangle, it'll be discarded before it's actually sent to the pixel shader. So we can make sure that everything that's sent to the pixel shader is more than or equal to 0 in the U and V. And as long as we know that U and V is less than or equal to 1, which again, these constraints are just saying if the point is within the triangle, then we can say that the point P is the point A plus a little bit in the direction of the AB line plus a little bit in the direction of the AC line, right? So what this means is we can describe those lines as B minus A and C minus A in terms of vertices, which makes this just easier to deal with. We don't have to calculate like a line equation or anything like that. And if we just expand that out and group like terms, then we get 1 minus u minus v times a plus u times v plus v times c is equal to the point P. And so that's how we use just u and v to describe the barycentric coordinates of this point P. And that's used in describing a location on a triangle so that we know what part of, for instance, the texture, what pixel in that image will map to that point. Okay, so I'm gonna I got a bunch of resources here, but I've got some things that I want to show you guys before I wrap up. It's been almost an hour of me just talking and showing you poorly drawn things. So I thought it'd be nice. Hey, maybe I can show you some code. So there are two things that I wanted to show you. I wrote a command line rasterizer in Rust, and so if I do, I think that's what it is. Oh, I shouldn't do it in that, should I? All right, I should. Oh, is it still running? Oh no, it's still running. I can open it in. Give me a sec. All right, Rust. Close that. And so this shows you in the command line. Whoops, I can't resize it because it depends on the size of the console window. Oops. It just shows you like some 3D geometry projected onto this 2D screen and it rotating in real time. If I open this again with code, then maybe I can actually show you the code because that's the important part. The tiny whitish dot. That might be the console cursor. So it's writing everything as characters to the console. Yeah. So there are a few things that I think might be of use to you guys if you do look into this code, which I have on GitHub and I link in the PowerPoint slides, but I'll put in the Discord Skillshare text channel at the end of this presentation. One of the things that's pretty useful is this is a good mathematical representation of the projection matrix. Um, and it sort of breaks it down. This is aspect ratio. This is the calculation of the field of view, and then view plane normalization is uh, done by this, and then it shows you the matrix itself here. It's sort of messy, the code, but there's this is the function that goes to normal that gets it to normal device coordinates. This is a function that scales things to view. This gets the projected triangles, and things like that. So it's all broken down into some of the different steps of uh, rasterization. Now, obviously, this program doesn't use the graphics card to do any of that. It does it itself. And that's normally called software rasterizing. So, what was I going to say? So, doing these things like projecting to the viewport and rasterization and stuff like that, uh, that's in most graphics programs, that's all automatically handled by the graphics card, because that's what the graphics card's built to do. There are certain non-programmable parts of the graphics pipeline, and one of those is rasterization. And then another one I think is color blending. The reason why they're not programmable is because it wouldn't make any sense to make them programmable, because they're meant to be generalized to uh, every possible instance you would have of uh, rasterizing points based on the input that it's meant to receive, and because it makes doing things like interpolating between the points of a given geometry, uh, it assures you that, or it ensures that that will never give back undefined behavior, because that's part of what uh, the graphics card needs to be able to do quickly, is interpolate between points. As I showed you with the barycentric coordinates, um, that's going from you know one. We're only defining the corners of each triangle, so to get the entire rest of the triangle, it needs to interpolate between each of those points. The other thing that I wanted to show you was this uh, this code that you can find on GitHub. It's called Tiny Renderer. It's a software rasterizer, and it's like a full software rendering engine, written in just C++, no OpenGL, nothing else. It's all just C++. And the GitHub repository has an entire like say, I don't know, 16 part tutorial on like how to write this thing yourself. But it's very nice. The All of the code's on GitHub. The uh, it even comes with some object files and stuff like that. And when I need to move this. Sorry. When you run it, where is this? Tiny renderer. Okay. You just run. I have to have this here so that I know the folder. Okay, so you obviously you have to build it first, but and so it'll take an object file and all of these other files that it uses for the textures and things like that. And it will output it to framebuffer.tga. And this is an image file that I guess the only application I can open it with is Photoshop. But this shows you sort of the output of the renderer. It's got everything from spectral like highlights to shadows to the everything. It's got a lot, and it's a very very small program. Yes, this is made all through. It's just native C++. You might have to add the algorithm include to a few of the files, because I don't know, I'm not sure why, but it was trying to use min and max without having this include. Yeah, it is. It's really crazy. And there's a whole where's it? It's right here. Yeah. It's not going to let me click on this. I think I have it open already in a different tab. I just have to find it. This is not that. That's OS research. Close that. I don't know. No drawing involved. Yeah, well, so the in this OBJ thing here, right? If we look at I'll open this in Notepad++. You've got these vertex, definitions here, right? Which are all there's a lot, and then you've got F for, I think that stands for face, but this describes the indices of the vertices, right? So you've got like the vertex positions, you've got the texture vertices, you've got the normals for each of the vertices, and you've got the faces of each of the triangles. And so normally you create those object files with like a 3D modeling program like Blender or Maya or whatever. But it's got a few of those already for you here. And then you've got like these images already as well, which are used as the textures or the well, so there are color textures. Sometimes there are like normal textures or normal maps, which are stored as textures, but they describe the normal values at certain positions, things like that. So all of these things, they're assets that would need to be created if you didn't download them. But I don't know why it do that. But all of the code here, you don't need any libraries or anything like that. You can just write it. Most of the time, if you're writing like a serious graphics program, I can show you in my current personal project. I'm using quite a few different libraries. I've got Asset Importer, GLAD, GLFW, GLM, which are all OpenGL libraries. SPD log, which I don't think I'm actually. No, I might be using it. No, I'm not. I don't know why I have this included still. SDB image, which is what I'm using to load image files. And I've got, let's see, so go to main test. Test 2 is probably better to show off. I should just build. And it'll take a while because I'm loading in large object files. And I'm not doing it like in parallel. But this is like a deferred renderer. I'm using OpenGL as my graphics API. And I've got each of these models and each of these lights. Normally, this many lights would be really hard, even on the GPU, but deferred rendering, normally forward rendering, you do everything all in one drawing pass, but with deferred rendering, you do a geometry pass that describes that puts like a bunch of information into 4 different frame buffers. Well, it's one frame buffer with 4 different like sections, and then you apply the lighting to that, and then you draw it all to the screen. And all of that is done in like, is this my largest? This is the H file. CPP. No, it's probably in here. Yeah. So you've got all of these like, well, this is 3. Do this. OpenGL stuff. Yeah. So like bind buffer, buffer data, bind vertex array, all of that stuff. Graphics APIs like OpenGL are necessary to interface with your GPU unless you want to write your own GPU driver, which I don't recommend. It's way more complicated than actually doing graphics stuff. But like there are a few different rendering APIs that are commonly used. OpenGL is one of them. Vulkan, which is made by the Kronos Group, who's the same. They're the same people who maintain OpenGL. That's another rendering API. It's notoriously like verbose and hard to get into. So I'd recommend going with OpenGL because it's a little more simple. And then Direct 3D, which is Microsoft proprietary, only runs on Windows machines. And then, or DirectX, I think it's called. And then Metal, which is Apple proprietary. So I think there are a few other graphics APIs out there, but those are the main ones. Um, and like graphics programs that are like meant to be rendering engines and stuff often become really long projects like this. But um, just using a rendering engine to make like a game or something like that doesn't necessarily need to be this big. They can you can draw cool like 3D animations and just a couple hundred lines of code, and I mean like only a couple hundred, like 200 or 300 lines of code. Um, have I worked with metal? No, I haven't. I don't actually have a an Apple computer. Um, I don't think I know many people who have worked with metal, but um, I gotta tell you, I could tell you all about OpenGL and Vulkan though. um, oh, I would say the OpenGL is a part of most um, applications like games and stuff like that. And WebGL is often what's used for web programming. Um, but for video games in particular, I know that there are often multiple graphics APIs that are integrated separately. So depending on the operating system you're running on, it'll have like an entirely different backend to interface with the graphics API um, that your system uses. OpenGL is the most cross-platform solution, though, which I think is also maybe why it's being used so much on the web. Um, graphics rendering and stuff, at least GPU-bound graphics rendering is on the web is very similar to. I think it's like the same thing as everything I've described. Um, it's just you would implement it on a web page with like some sort of like canvas or whatever to display all of the graphics and stuff like that. You just use like some library like uh I I know 3.js is a pretty popular one for um more intense graphics programs, but like I think and I think you can connect that with React as well. I think there's a library for that. But it's even if you're like mostly if most of what you do is web programming, you can still get into graphics programming. Graphics programming, I think, without having to like download Visual Studio 2019 and um, like compile everything in C++ and like you know figure out how to set up your uh, make build system or whatever. You can still do a lot of it on it with web APIs, which I think is great. And I think that's about it for what I had to show you guys. I'm gonna finish up by sh- like talking about the resources here. Um, so I already talked about Tiny Renderer. Um, it's it's a great project if you want to look more into the bare bones and like lower level theory behind how rasterization works and stuff like that. Um, uh, Brian Will on YouTube has an OpenGL playlist. Uh, the first like 3 videos are all very theoretical and stuff like that, and then the rest of it is talking about how to um, create a graphics application with the OpenGL API. Learn OpenGL has almost the exact same content as Brian Will's playlist, because I believe Brian Will pretty closely followed the Learn OpenGL like sections in order and stuff, and used much of his content, but added a lot of his own notes to help explain things a little bit further. But this is all this is like a blog all written uh, quite a good while ago, but it's all still relevant. And there's a lot of content on there, all the way from very, very beginner to pretty advanced graphics topics. Real-time rendering resources is just a gigantic collection of every link you would ever need to any graphics resource ever. And it's related to the book Real-Time Rendering, which is a very critically acclaimed sort of book in the graphics programming community. OpenGL tutorial is a kind of like a PDF version of Learn OpenGL, but it's got more theory behind it, and it teaches you a little bit about like linear algebra and stuff like that. So it's pretty good. My command line rasterizer written in Rust. Again, all of these things will be linked in the Skillshare channel and Discord after this. And I'm a pretty good resource too. I've got more bookmarks than I know what to do with. So if you need me to point you in the right direction for any sort of graphics topic, I probably can do that. You can message me on Discord. My Discord username's MyGoodSir number 2011. On the Software Engineering Club Discord server, I'm just named Joe Adrian. And I've got a nice little blue name, so I stick out, which is nice. And you can also email me at my Towson email address. That's the email I check most often. So, yeah, that's about it.